Hello. Okay, so today we've got Rob Dawson, who is going to talk about peer-to-peer protocols and networking in Ethereum. So this is going to be fabulous because this is going to be one of the first talks about this level of the overall Ethereum stack in the world. So I would say so anyway, given the availability of information anyway.
Yep.
Yeah. So it should prove to be very exciting and very interesting. And so please take it away, Rob.
Okay. That's big words to live up to, but I'll see what we can do. There'll be a lot of information at least that might not be available elsewhere. Whether it's exciting and interesting, well, we'll see. Okay, so before I dive into any detail, I want to give special thanks to Raul Kripalani, and he's one of the protocol engineers in Pegasus that has done and Consensus. So Pegasus is the group that I work for within Consensus. And Raul has done an awesome amount of work in actually doing some implementation work with Dev P2P, and so has been answering a lot of my questions and helping me to come to the real sort of understanding, pointing me to the right spots in code. So yeah, he's a real expert in this stuff, and I'm just, I don't know, I'm learning and presenting what I know, and so any mistakes in these slides are mine. Anything that's good and useful, it comes from Raul. So it's going to be a tale of two stacks. Okay, so the Dev P2P and the networking layers inside of Ethereum, there's two things that are happening that we want to sort of keep in our heads. So if we look at the boxes there and the sort of networking stack diagrams that look sort of familiar to networking stack diagrams that you will have seen all over the internet before. We've got the discovery sort of side there, which sits on top of UDP. And then in parallel with that, we've got the actual wire protocol that's happening where things get sent around, blocks get sent around, all the peer-to-peer sort of messages that are happening on your ongoing peer-to-peer network are happening. And so that sits on top of TCP/IP. So the two things that are sort of happening with our stacks, you've got the discovery, finding all the nodes and people that you might want to send messages to, and then the work of actually sending the messages and communicating. David.
I hate to be a pedant. That's not really true. I love being a pedant. But I hate to be a pedant on your first slide. But technically, that would be TCP, UDP, and TCP IP, or just UDP and IP.
Sure. Okay. Okay, so the discovery, which runs on top of, I'll get it back, UDP IP, is what's used to build the peer-to-peer network. And it's a Kadima, gotta get that word right, I'm going to be saying it a lot, a Kadima-based protocol. So I'm going to get into the details of what that means. So Kadima is a peer-to-peer protocol that talks about being a distributed hash table. So it's for, I guess, your normal sort of peer-to-peer type network where you've got bits of data that you want distributed across the network, and you want to be able to get data from a hash table, so like your standard kind of hash table that you think of in programming. You want to be able to store things inside that hash table and get them out. So that's what Kadima does, and so it has that hash table that is distributed across the network, provides, importantly, some of the node lookup and how to do the routing and the structure of the network. So telling nodes which other nodes you might be interested in knowing about. I say that sort of network structure and network topology part is really important because that's the bit that Ethereum uses. It doesn't actually use the key value store part of the distributed hash table that Kadima talks about. So it's a well-defined protocol. There's a paper that talks about the details of Kadima, which you can look up. Actually, an open question for the audience?
Yeah, I have a question on this. So we've had a lot of discussions around this, including with Raul, and it looked to me like it doesn't use the DHT. It looks like the implementation each node keeps its own network structure internally.
Yep.
Mm-hmm. And I wonder why. Do you happen to know why Ethereum doesn't just make use of the DHT? Was it a security concern, or?
So it's
Is it centralized?
So the DHT.
Maybe.
The DHT part of it is the actual storing. So the Kademlia having the two parts, so it has the routing table.
Yep.
So that part of it, Ethereum does use.
Mm-hmm.
And then the DHT for key value store,
Yep.
it just doesn't use that at all.
Does it use the DHT for the routing table? Does it share the routing table around the nodes?
The routing table is implemented the way that Kademlia specifies it works. So the routing rules are as per Kademlia.
Yeah, that matches my understanding, and yet I still don't know how to answer my question. So I guess I'll.
Yeah, and so the DHT part of it, like the actual key value store, just not implemented at all. So I'll keep talking through Kademlia and how the parts of it that filter through to Ethereum, and that might start to answer some of your questions. But I guess it's, yeah, and it might be a conversation for offline as well. Okay, so a Kademlia routing table. So this is the magic and the thing that Ethereum really uses within its discovery. So it's just a table divided into buckets where each bucket holds nodes at a distance from that node. So where the definition of distance is actually not related to any network physical distance or anything else, it's just an XOR of node IDs. And so Kademlia specifies, I think, that the distance is by least significant bit, whereas Ethereum ends up implementing it by most significant bit. And implementation details, I don't know a strong reason why you would care one way or the other, because the node IDs that are used there by Ethereum are Ethereum cacacs of the node. So it's just a hashed data structure that's being used with that.
Is there some magic about the way the node IDs are assigned?
Node ID is derived from the public key. So
yeah, right.
Yeah.
So no.
So no.
They're completely disconnected.
Yep. So there's no magic, no real reason why you care which way it's being XOR'd, and the actual routing table that's being used there, again, it's the distance from us. The peer-to-peer protocols behind the scenes will use give the weighted sort of preference to different nodes, and that preference about which nodes they'll send messages to or prefer is separate to this sort of routing table that's sitting there. Okay, so the Kademlia protocol supports the following 4 messages, each with an appropriate response. So it's got a ping, it's just a simple straight ping with pretty much an empty payload, or I think it's got like a 1 byte payload inside the Kademlia message. The find node, so that's going out to a node, and it actually, in a lot of the work for Ethereum itself, it'll talk about that being more of a find neighbors, where you'll give it a node ID and you'll get a response back being a list of the neighbors to that node. And that's the same semantics are within that find node there. The store and find value, I'm listing here for completeness, but these store and find value are not implemented in the Ethereum discovery. So the store is storing, that's the actual hash table part of Kademlia. And I guess the reason that the routing table was used from Kademlia is the shape of it was kind of they liked the properties of that routing table. So when you're bootstrapping within Kademlia and you want to join a network, you'd connect to a bootstrap node, you'd go to that bootstrap node and give it a find node for myself, and then it would give you back the list of nodes that are close to you. And then from that, it's going to then refresh its own buckets, looking up random values on the network and asking for it to give nodes and things back. So that's the bootstrapping process within Kademlia.
Sorry, so at that point, once it issues the find node request of itself to its bootstrap node.
Yep. To a bootstrap node, yep.
To a bootstrap node. And then the return value there is
going to be a list of the nodes that are close to you.
Right.
by the distance algorithm.
And so is there then a recursive find node set of operations on each of
I
those?
think that's probably going to be happening within the Kadima
Yeah.
world as well. Yeah. Okay, so how this works in Ethereum. So we've got the ping message that I talked about briefly, and then it's got the responding message, which is documented as a POM. It's got the find node message, which in the rest of this talk I'm going to be calling it find neighbors. And so one of the things that I've been sort of mentioning with various people from Consensus earlier is some of the nomenclature around everything is not great in the Dev P2P protocol. And so there's an intermixing of find node versus find neighbors versus find nodes versus the message naming is not consistent. But most of the time, it ends up being, and the code often, usually reads as find neighbors across, I think I was looking at 3 or 4 different client implementations to get the details of how it actually really works. So as I've been mentioning, Ethereum does not implement the store or find value operations that were specified in the Kadima paper. So our discovery. So 2 sets of paired messages that we've talked about that I'm going to sort of be reiterating myself from time to time because that's how we're going to learn and get our heads around this. So the ping and the POM, the find neighbors, which the responses are neighbors. The other thing that's interesting is that all the messages are signed with the node's private key. So everything that's being sent is authenticated. Another concept that is in Ethereum that is not in Kadima is the concept of bonding. So this bonding idea was brought in to help protect against some DDoS attacks against the Ethereum network. There's some questions about whether how good of a move it really was and how effective it's going to be, but it is there, so I'll talk about it. So the idea is that you need to, before you can do find neighbors and you have to respond to find neighbors, you must have done a ping and pong. The thing with doing the ping and the pong is it's going to give you that you've got a proper private key, that you are a real node. People can't just flood you with messages that are sort of sitting there. Okay, so what'll happen is you'll receive that ping and pong pair of messages, and then as a part of that, you'll potentially add people to your routing table, or you might say, oh, I've already got enough nodes that I'm quite happy with, so I'm not going to add you to my routing table. And so you would then drop that node, and messages then that aren't in that routing table from nodes in that routing table will be ignored. So the overall message format of what's happening with the messages that are being sent here, there's a type and some data, and then the signature and hash of the signature, type and data. So this is the message packet that's being sent as a part of the Kadima across that UDP connection. So the data is what's being sent as a part of those ping, the pong, the find neighbors, and the neighbors. So I'll talk through just each of those messages again and each of the pairs. So we look at the left. So you send a ping, you get a pong back. So the ping is used to, rather than just always as a straight ping and pong, like keep things alive, they've got that little bit of extra stuff that they're doing to help initiate the bonding process. The data that matches the data that we talked about in our previous slide that's being sent with the ping is the from, the to, and the expiry of the message. Once you've done a ping, the people that are listening to that ping can sort of say, okay, yep, you're a valid node, I'm going to add you to my routing table. On the initiator, they need to wait for that pong to come back and to be successfully completed, and have that to add them to their routing table. So the data in a pong is the hash of the ping to make sure that it's a valid a valid sort of message and that you're ponging back to a real message, the to and the expiry.
Sorry, Rob.
Yep.
So, yeah, so there's a successful bond on receipt if the hash matches.
Yep.
There's no check in the signature or any of the rest of it, just is the hash?
So there's going to be the, I guess, the standard sort of validation of the message itself with
Yeah.
the signature.
So
and
it's
things that are
going
happening.
to recalculate the hash and compare and then validate the signature and unpack successively?
So
Yeah, but that's ping hash. So you, in other words, you've hashed what was sent to you and you're sending it back to have correlation.
So the hash that's being sent there, the sender is validating so the person who sent, so if I use the words initiator and responder, so the initiator sends a pong to the responder, sends a ping, to the responder, which will include the hash. The responder will send a pong back to the initiator. Within the body of the message that they're sending back to the initiator is going to be the hash from that ping message. And so when the initiator receives that message, they would first check that it's a valid message by looking at the EC signature and the hash of the pong message that was sent and say, yep. And then it would go inside the payload of that pong message and look at the ping hash and confirm that the ping hash matches a message that they sent, that the initiator sent to the responder.
Got it, thank you.
Okay, so that's the ping and the pong used for bonding. After you've bonded, then you can send out a find neighbors, which matches the find node kind of call in the Kadima paper. So find neighbors is going out and saying who are the neighbors of a node. Is essentially the semantics of what's happening. So I'll continue with my initiator and responder. So I'm going to stand here and be the initiator. The initiator sends out a find neighbors for a node on the network. The responder is going to hear that message, look at the target node, say, do I have that target node in my routing table? Yes, I do. Okay, here are the neighbors that I know for that node, and give that back to the initiator as the neighbors call.
So the list of neighbors for the bootstrap node and the list of neighbors for the new node that's joining would be completely different because they're XOR comparisons based on their two enode addresses.
The
hash of
different. Hash of the enode addresses, yep.
Yeah. So they could be completely different. They could have a completely different list of neighbors and a completely different closeness order.
So the neighbors that are sent back are the neighbors of a provided node. So you're sending back so if we say initiator bootstrap node, so the way that the protocol initiation sort of view is going to happen is the initiator will send to the bootstrap node, what are the list of neighbors for me? The bootstrap node is going to look at its routing table, do the lookups to be able to see that using the XORing sort of distance algorithm, and then provide them back to the initiator. And so the node list that it's giving back to the initiator is going to be the ones by distance that it knows about. And so you could then, as it does the discovery around the world, end up with a completely different set of nodes in your routing table to anyone else.
Yeah, okay.
Okay, so the key thing that Ethereum does then is when it receives the list of neighbors back, it'll do the ping pong bonding process that we saw in the previous slide to make sure that they are actually alive and real nodes that are working. Okay, so I've just shown and demonstrated the bootstrapping process. And a thing that's worth noting is that most clients will optimize the results, will store and persist their routing table so that they don't, we don't packet flood the bootstrap nodes. So to sort of minimize the amount of messages that are being sent to the bootstrap nodes, particularly because most clients have, on mainnet, have a hard-coded list of bootstrap nodes. And so, yeah, you sort of want to respect the fact that those nodes are going to receive a lot of traffic unless you do something to stop. Yep?
If the bootstrap nodes are hard-coded, and I guess that's just a limited number, isn't that some sort of single point of failure? So if they are gone, the bootstrap node, then no node can join the network anymore?
Yep. Sorry. Yes, that's a fair observation and a good one. That's why most clients persist that node table. You could within your clients configure it to use different bootstrap nodes as well.
Follow-up question though is, how many bootstrap nodes are there?
So the number that I remember for bootstrap nodes is 5. Is that a number that matches your expectation?
Yeah, it's something in that order. So it's not like there's, you can just drop a nuke on, like, I don't know, New York and you've wiped out the bootstrap nodes.
Yeah, so there are 5 of them. They are well known as current, I guess, somewhat centralization points. And so they are well hardened and kept up and well maintained to be that.
But we are 5 cruise missiles away from losing Ethereum.
Not quite losing Ethereum. Making it, you're five computer failures from it being hard for new nodes to join and bootstrap Ethereum without client changes.
Yeah, and if you did lose 2, say, simultaneously, and there was some reason that they were permanently off the air because the companies that operated them said, actually, this Ethereum stuff's going nowhere, we're out of here, then you could do a software update and have new boot nodes.
And so the e-node addresses, the bootstrap nodes are embedded in the client code? Is that what you're inferring?
Yes, it's a bit like CA certificates being embedded in your web browser. Similar sort of concept. Okay.
And clearly there's better things that could be done with that than a hard-coded list in clients. But yeah, I pictured that a client that might be coming from Consensus would have something different in it. So periodically then there will be a task that's running on clients to refresh their table. So by periodically within Geth, I believe this is about sort of hourly, sort of sitting behind the scenes. Other clients, it's up to the client to say how often they want to do it. I'm just going to go to the next slide. Okay, so there's more differences between Ethereum and Kadima. So that ping pong sort of bonding that I talked about, the most significant bit versus the least significant bit for distance between nodes. Within Kadima, it specifies a reputation sort of algorithm and says that the reputation is just based off how long a node has been connected. Within Ethereum, the implementations typically use something a bit smarter, but actually they're not super smart, but they should be smarter. So there's a lot of talk about your reputation between nodes being based off what sort of blocks you're getting back, whether you're getting repeated blocks back, and that kind of information on the actual TCP/IP stack. But in practice, most of the clients actually don't do too much magic around reputation at this point. Okay, so that's our discovery process that Ethereum works with. I'm going to move on now to the Dev P2P stack and the actual ongoing communications that are happening. And so the words Dev P2P, discovery, RPLx are not used consistently across the documentation that's out there. And so forgive me if I get some of the concepts a bit jumbled. I'm just preparing you for what you're going to see out in the world. Okay, so Dev P2P and the ongoing communications that we've got happening. Sitting on top of TCP/IP, there's an RPLx. So RLP, oh, there's a typo on the slide.
Yeah.
It's RLP, not Ripple. So RLP being the recursive length prefix encoding format, and RPLx being a networking communication layer that's built on top of that, which I'll dive into some more details in a moment. And so I'll hold questions, and then after I've shown the slide, and then I'll show the slide, and I'll take questions on that. Then sitting on top of that is the wire protocol, and then sitting on top of that are the sub-protocols. So sub-protocols being ETH, so the main sort of Ethereum protocol for doing the peer-to-peer distribution of blocks, things like Swarm and Whisper, and there's a various light syncing sort of protocols and things. So it's those sub-protocols are there's a easy-ish way of being able to extend and build your own sub-protocols, which if I had an extra 2 weeks, I probably would have implemented one and showed us the code for how to do that, but I didn't have an extra 2 weeks, and I've got lots of slides anyway. Okay, so I'm going to go through each layer in that stack now, except for TCP/IP, because hopefully that's base knowledge. So RLPX, some of the properties that RLPX provides to the higher layers. So it provides encrypted multiplexed messaging. So that's a fancy words. So the multiplexed just means that the headers of the RLPX messages, one of the first sort of sets of bytes in those are going to be what message type it's going to be, which protocol it belongs to, and then which sub-protocol it belongs to. So it sounds really fancy that it's multiplexed, but I guess it is, but it's not really that magic. The encrypted, there's a key establishment very early on in the protocol that gives you some keys that you'll be able to use for encrypting the messages and providing authentication around it as well. The first step that we see in it is going to be there's a session that's initialized, so there's ongoing session. I'm just going to wander over here. No, it's good. So that's a session is initialized and kept ongoing. So with the first part of that initialization of the session is a cryptographic crypto handshake. RLPX also provides the messaging of same message framing and the multiplexing of the sub protocols that I've mentioned. I'm going to dive into the session initialization. So this is where it starts to be a little bit blurring across the protocols. So RLPX, at that layer, there's the initialization of the session, but the session's actually not really initialized until the initial wire protocol messages are sent. So there's a crypto sort of auth handshake that happens first, and then within the wire protocol that sits on top of RLPX, there's these two hello messages that are sent, and then after those messages are all sent, then you actually, we've got a session that's working. That is kind of the RLPX session, but it's kind of the wire protocol session because there's that little bit of a blurring of the lines there. So the crypto handshake consists of an auth and an auth ACK. The auth message so the initiator will generate the secret sort of stuff that's sent across and send that across as an auth message, and then the remote will look at the data that's sent in that auth message packet, in that auth message, and then it will respond with the auth ACK. After that's happened, and so this can be sort of communicated, the hello messages are both sent at the same time, sort of aggressively to each other, and is able to derive the secret sort of information and the shared sort of data from the initial auth and auth ACK messages, and is able to send the messages across the wire protocol as a hello message. And so it's able to do then, that can sort of be talked about as the protocol handshake. And so this protocol handshake can be now authenticated. So when the initiator sends the message to the remote, when the remote receives that hello message, they can confirm, hey, all of the data that you sent, it looks right, we're all good, we'll keep going. And vice versa on the other side. So that hello message consists of this kind of information. So the protocol version that you're running, so that's the wire protocol version, it's going to have your client ID. Importantly, it's going to have the list of capability and capability version tuples. So these capabilities are the sub-protocols that you support. So I'll come up to a slide hopefully shortly, and we'll have a look at that, but that's essentially saying I support the ETH sub-protocol version 62, for example, or the Swarm protocol and version 1.
The client ID, is that like, I don't know, Geth is say 2?
Yeah, it's probably going to be more than, yeah.
And, alright, yeah.
Okay, so so that hello message that we've just sent back to them is then going to trigger off each client is going to do on its own side the sub-protocol negotiation and initiation. So the initiator will send to the responder its hello message. The responder, on response to the hello message, will be able to look at it and say, here are the list of sub-protocols and the versions that they support. So it might be 3 different sub-protocols and it supports 2 versions for each of them. It's going to compare that list against what it knows that it supports and what it knows that it works for. And then for each sub-protocol, it's going to pick the highest version that's common between the 2 and say, yep, that's what we support. Independently, the responder will assent to the initiator, hopefully the same list that it's going to actually really support, and it's going to do the initiator will look at that and do that same sort of matching algorithm. And so they should, assuming that they've both been truthful about the messages that they're sending to each other, come up with the same list of sub-protocols and version numbers that they support. So each client, after they've received that list, is then going to send off essentially a hello message optionally for each of those sub-protocols, depending on what the sub-protocol specifies. And so in the F sub-protocol, it'll send a status message, is what it'll send through. Okay, so that so that sub-protocol negotiation is wire protocol. When it sends that handshake there, that handshake then is the sub-protocol that sits on top of the wire protocol. So going back to the full set of stuff that the wire protocol has. So the hello message we talked about, then there's also a disconnect, a ping and a pong. So hello, we've already talked about this. Disconnect is saying I want to disconnect. I want us to disconnect from each other, and it includes a single byte reason code, where the reason codes are there. Just for completeness, I'm not going to talk to each of these.
I was just laughing at useless peer.
It's interesting the amount of information that's being leaked, like even client ID.
Yeah.
Like if you look at it in transport layer security, that sort of thing's gone because they realise you're saying, hi, I'm this, I've got these vulnerabilities, please attack me.
Right.
So you don't say what software you are, if at all possible.
Yeah.
Yes.
So
these are all going to change undoubtedly over the years as the protocols evolve and people learn that there's a lot of vulnerabilities that are sitting there. Okay, so the ping is just a keep alive message. the ping and the pongs are used to keep that session alive. So it's just you send a ping, you send a pong back. Our sub-protocols. Okay.
Is there any circumstance in which a ping and a pong is actually sent? Why does one node send a ping to the other at this wire protocol level?
Again, it's just to keep alive of the session. So,
okay.
Yeah, it's just periodically they will do it if there's nothing else happening.
Yep.
Maybe it's been disconnected for some issue in the past and it wants to refresh its session.
Yeah.
So a good question, which I can dive into some code and come up with a better answer.
Yeah. Okay. Go on. Yeah. I'll do it myself.
Okay. So the ETH protocol is the main sub-protocol that is implemented by pretty much every client. You're not going to be really an Ethereum client in a part of the mainnet contributing to the peer-to-peer distribution of stuff unless you've implemented the ETH sub-protocol. There's a bunch of versions. So there's some versions that start at like 1, 2, 3, 4, and they're like the early sort of testing and early iterations of the Ethereum. And then there's a big jump to I think about 61, which is kind of the first version of the ETH sub-protocol that was really being used heavily out there. And now clients support 62 and 63 as sort of the versions that they work with.
How often has the version been bumped recently? Is it slowing down?
It's slowing down. So that big jump from 61 to whatever was before, that was like they missed 40 versions. So while the versions look like, there's been lots and lots of versions of this protocol, there's a gap of about 40 versions there.
Did they hire somebody from Sun?
Maybe.
Yeah, probably. So my understanding of the rationale about having 62 and 63 is that, say we want to, say 64 comes out, then one client initially is only going to support 64 and everyone else is going to support 63, and then eventually people will incrementally roll out version 64 so you can talk two versions and negotiate. Fair enough. Given 63's been out for a very long time now, would it be viable to just say, hey, we're not going to support 62 because anyone who's trying to connect with 62 is probably hacking?
So it's possible. The main reason why I think 62 and 63 are out there is because 63 is a straight additive on top of 62. And so everyone wants to say, I support two versions, so I'm going to support 62 and 63. The change between 61 and 62, there's a lot of breaking changes and a lot of difference there. So if you support 63, you by extension you support 62. So that's why.
Yeah, it's no cost.
Yeah, there's limited cost, I guess.
Yeah. Testing.
Okay. So the ETH flow, I think we've talked about this, that we see, so I'll do it again. So it starts at the crypto handshake at the RPLx, then you'll have the hello messages being sent at the wire protocol, then that's going to initiate the sub-protocol, which is ETH, and so the way that ETH will start is both sides, the initiator and responder will both send a status message. After the status message has come through and they both sort of accepted that properly, the protocol will continue and they're able to send messages to each other.
Is there anything in that status? What gets communicated?
I will get to that momentarily.
Alright.
Okay, so there's the collection of messages that form the ETH sub-protocol. And so this, I'm going to go through each of these, and then that's probably the bulk of what I'll be talking about, just to set expectations and mental sort of areas. So these are all the messages that on the left, this list here, the first set is the version 62, and then the version 63, as I mentioned, it's all of 62 plus these extra couple of messages. So the status message, and this information is taken pretty closely from the documentation about the Ethereum protocol, and so you can Google it and find this and more. So the purpose of the status is to inform a peer of its current state, sent at the sort of initialization of the protocol, and so giving the protocol version, the network ID. So network ID is which Ethereum network you're operating as a part of. So it would be expected that the network ID for two clients talking to each other should be the same. I guess the best hash is the hash of the most recent block that it sort of knows is a good block, and then the genesis block that was used for that client.
So given though that, if we think about the handshake which has happened thus far, except I guess, so different networks should have different boot nodes, I guess.
Yep.
So, yeah, right. So
Yeah.
so really, if you were using the wrong boot nodes for your network, then you're in trouble anyway. And I guess this network ID is just idiot-proofing it.
Yep.
Yeah. Okay.
So new block hashes, useful for specifying new blocks that you know about, or giving the hashes of the new blocks that you know about. It should only be announcing the hashes after you are sure that they've been validated, so that you've gone through and done a validation of the block, or you've received them from a client that you really trust and you trust their validation of it. It should be, so there's a should there that I've got standards guys sitting around me. I think I can see them all smiling.
Or it's not in capitalization.
Yeah. And that should be a capital should, and it should not include blocks which the peer knows about. So it's okay if you do, but you're probably going to take a reputation hit if you keep on. In theory, you should be taking a reputation hit if you keep on telling people again and again, here's the blocks that I know about, here's the blocks that I know about, here's the same blocks that I know about, here's the same blocks that I know about. This is meant to be telling you, here's the blocks that are new for me that I haven't told you about yet. And how that's done, it's up to the client. I guess the thing that is there is that you might actually miss sometimes telling someone about new block hashes that you've heard, so it's okay to not always tell everyone everything.
So the requirement there is you don't have to keep an internal state remembering what you've told exactly each other node.
Yep.
Yeah,
exactly.
That makes sense.
So the transactions. So these are kind of, I guess, almost preemptive sort of messages that you're sending out to peers. So you're not sending these messages back in response to someone doing it. You're just going out there and saying, here's the new block hashes that I know about. Here are the transactions that I know about. And here's the more sort of query type layers that are happening with it. So the sort of request response type messages that you're going to have. So there's a get block headers. So an initiator might send to a responder, get block headers, and the responder's job is to send back block headers. So you'll see, next slide is the block headers. So it's the request that you're sending out, you say, here's the maximum number of headers that I want to receive. That skip is a number that you're sending back to say, send me every 10th header, for example, or send me every 100th header, like only sending me like periodic headers back, so that you can sort of do some smart stuff then maybe with the syncing. The reverse is used to say, okay, I'm giving you a hash, send me the ones that are either forward of that hash or behind that hash. And again, using that sort of skipping is factored into that. So it might be, say, send me each 10 blocks ahead of that hash, or send me each 10 blocks behind that hash.
So this is to assist in finding things like forks in the
Potentially, yeah.
in the tree.
Yeah.
Yeah.
Or maybe some smart stuff that you're doing with your syncing as well. So block headers is the response to get block headers. The response is an RLP encoded list of block headers. The format for what a block header is, you can read the yellow paper for fun to see what a block header is meant to look like. The next that sort of goes with the idea, you know, you've got this get block headers, you're going to want the actual bodies for those as well. And so it's specifying the set of blocks that we're interested in with hashes, so giving it that. So in response to the get block bodies, so you do a get block bodies and then you've got to give back the block bodies message. It's the blocks that are in response to that without the header, and the blocks are match the hashes, and it's possible that it actually doesn't have the blocks as well.
Sorry, can you go back to get block bodies, please?
Mm-hmm.
Or one more.
One more? Yep.
I see. Okay. Thank you.
So new block is again it's a more sort of aggressive sort of message that's being sent out to the network, that you'd be sort of publishing out, hey, here's a new block that I've got. I guess it's going to probably used by a miner or maybe other nodes in the network, but really a miner wants to be doing new block as quickly as it mines something. It wants to do that new block to say, here's the new block. And then, you know, the other nodes are probably going to propagate it out to the rest of the network as well. Get node data. So this is one of the first of the version 63 messages that's new in version 63, and the rest that I'll talk about will also new in version 63. And so get node data that requests to get some node data. And so this is wanting to get data from the world state of the node. So wanting to be able to sync some of the data, getting the data about the accounts or the nodes or states to get information that you want to get. And so you say get node data, the response is going to be node data that comes back, and that's going to give you the values in response, and it's a best effort, so it's the data that you know about. Get receipts is again that request. I want to give you asking for you to give me a receipts message. Give me a list of transaction receipt hashes that you want to look up, and it's going to give you the list of transaction receipts back. So that is the ETH subprotocol. And that's the most detailed subprotocol that I'm going to get into now. Now I'm just going to quickly gloss over some of the other subprotocols, not even get into any of the messages of them, just talk about what versions are sort of out in some of the clients. So the lighter Ethereum subprotocol, LES, version number 1, hasn't really gone too far. I think that instead of using some of the more specific sub-protocols there, stuff has been added to ETH to help syncing more. Next one, Whisper. So Whisper is for sharing files and binary objects. The cunning name for Whisper is with versions 2, 3, and 5 out in the sort of supported versions by various clients. Swarm is the swarmy kind of name, which as implemented in Get, you can see that the version that's implemented there is version 0. So it sort of gives a bit of a hint to how mature this protocol is. The idea for, sorry, I got that wrong. Whisper is for doing, I guess, like a peer-to-peer type network communications or group-based communications. So
Off-chain.
and doing it off-chain.
Yeah.
So it's, I guess, think about you want to use your Ethereum peer-to-peer network to do WhatsApp is kind of my mental model for what Whispering is offering.
So Quorum uses Whisper, for example. Right?
Yeah, for some of its stuff, yeah.
Yeah.
Swarm is a swarm that works together to store large objects.
Sort of like IPFS.
Like IPFS. Okay, so that's kind of drawing to a close of things. We've been talking through our two protocols that form things. So our discovery protocol, which is on UDP over IP, and then the sort of network, sort of more runtime protocol that's happening with the messages, which is sitting over TCP/IP. There's the RPLx layer that helps to do the multiplexing and which provide the core sort of authenticated messages that are being sent through the wire protocol. Wire protocol making available the services to the sub-protocols. So that's our two protocol stacks that sit behind the peer-to-peer networking for Ethereum. And I'm going to do some ads. So tonight, the scaling of my picture hasn't worked great, but to let you know that there's another Ethereum meetup group tonight that's talking about smart contracts. URL is there, but if you just Google how to hack a smart contract Ethereum, you'll end up with the page. And so Lucas, who's at Blockchain Australia, he's also a consensus person. He's going to be talking about some security best practices, talk about how Solidity can go wrong, and there's many ways. So he's going to do a subset of the things that you can do wrong in Solidity and leave security holes. And that'll be tonight.
Where is it?
Valley Iconic.
Thank you.
757 Main Street.
There you go. So, yep. And yeah, so if you Google that or you end up at that URL, there'll be the details. I think it's a 7:30 start, but don't hold me to it. The future talks, series of talks for this group. So 2 weeks' time, there's going to be some talks about current research from some of the universities, and I think actually probably mainly from a couple of students who are doing some work.
So there's going to be myself from UQ. There's going to be a gentleman from Griffith University talking about wine supply chain, and there's some students from UQ who are also working for Consensus who've done a networking interceptor for Ethereum that works with Wireshark. So that should be, so those are going to be the 3 talks.
Do we get to tell QT they need to pull their game up?
No, what we should do is we should blame me for I've reached out to a few different people at QUT, but I did not reach out to enough people at QUT. That I take that on board as a deficiency in myself and not QUT. I should have been more aggressive at
Because I
asking.
know they're doing work, but maybe we can schedule another one later.
Oh yeah, there's going to be, so there's one of these current research things each 6 months. So,
Okay, so
more opportunities.
So 2 weeks' time is current research. 2 weeks after that, there's going to be learning about Solidity, the Solidity programming language. So that'll be Lucas presenting that. 2 weeks after that, a security and crypto talk, which Peter will be taking us through. And then 2 weeks after that will be a talk about consensus. And so that'll be either me, or we're looking at probably forming up a team in Australia within Consensus that's going to be looking at consensus. So that's consensus with the U there. And so that it'll either be me or someone from that team talking about it and talking having looked really closely at some of the consensus mechanisms.
You know, we could do another talk at some point on all the enterprise and consensus algorithms as well.
Yep, and some of those might sneak in
Some of
there.
those will be in that PLA.
Yep.
Yeah, but we've got IBFT and we've got
Yep.
RAMP.
Yeah, exactly. So some of those will be in there.
Yeah.
So just want to throw up a quick couple of acknowledgements, not announcements. So just want to give thanks to Peter, who's given me some feedback on slides, to Raul, who everything that's right in that slide deck is from him, everything that's wrong is from me. And Team Anzac, so that's the Scrum team that I'm a part of, and they've given input and time to help do it. That's it. Any questions?
I do have a question. Can you go right back to slide 12 or 10 or something right around there? So,
And I'm going to pause your question.
yep.
There's a non-consensus question,
Oh,
which
do
I'll
it.
take first.
Do it.
I was just going to ask, in each sub-protocol, there's nothing that specifies like amount of, say, like block headers or something like that. How's like the length, like the limit defined?
So,
Because I assume you can't send like 1 million block headers.
yep, so the get block headers, there's a max headers.
Yeah.
So, yep, and I'm not sure about the sizing, but I'm
Presumably clients could ignore
Clients.
max headers above
Yeah.
a certain
Yeah.
amount.
Yeah, well, my understanding for most of these things, like when you say, tell me about your nearby peers, a lot of these things are, you give it back as many as you'd like to give.
Yeah.
So it's up to really the client to work out how much
Yep.
it's prepared
So
to give
yeah,
back.
and it's, I guess the key thing is there's a max headers. So it would be, the requester would say, here's the maximum that I want back, and the person who's sending it would say, yeah, you said 500, but I'm going to give you 2. You want me to keep going backwards?
If you would.
Which, about what?
12, maybe? I'm guessing now. So,
What was the topic?
yeah, so really, when we're talking about the discovery, maybe you can go back a little farther. That's what I want to ping, keep going.
Go backwards.
Discover, okay, somewhere in there. So, if you've got a very large number of nodes, right? I've heard 10,000 or so, right? So you got 10,000 nodes. Everybody's got a different public key, and they're random. And so you don't know what you're going to get, but you could have, the hash of those public keys could end up being the most significant digits might be widely variant, right? And so when you do your XORs and compare, you might have clusters, statistical clusters within that address space, within the hash of the hash of the key space.
Possible.
And so if you have this very large number of nodes, and you end up with these statistical clusters in the space.
Yep, so probabilistically if the hash function's good, there shouldn't be too many clusters.
Yeah, maybe.
But statistically,
Yes.
you will end up with
And
clusters.
then you have a much smaller list of routes that are held by each node. They're ordered based on that XOR of definition of closest. So couldn't you end up with nodes where just by random chance the hash of the key gives it a closeness calculation that just means it never gets any traffic. It doesn't end up, a node doesn't end up in any routing table.
So I will point you to the Kadima paper, and they have proofs and discussions and things by analogy to say this is why it works, even with those statistical outliers. So in theory, yes, but in practice, no.
Got it. Okay, I'll read the paper.
Yeah.
I've skimmed it, but I need to go back and properly read it. It might be an airplane job for next week.
Yep. Other questions? Comments? Okay. I'm done.
Thank you.
Thank you.